Hello, my name is Ivan and my project attempts to solve a subtask of question answering, namely answer type prediction. For example, given a query of the tennis player who wore denim shorts, the goal would be to predict human, athlete, professional tennis player, etc. This task is important because it's known to significantly improve the quality of information retrieval based question answering systems like Watson, and it's also attainable because the neural network does not have to store all of the factual knowledge about the world in its weights or memory. To describe the problem statement more precisely, we have a query. Some of its tokens are also types within a certain type inventory. For example, movies about presidents contains collections movies and collections presidents. And the query has correct answers. For example, All the President's Men, which is a movie but also a political thriller, and Abraham Lincoln Vampire Hunter, which is a movie and also a vampire movie. Now, we define the correct types to be the intersection of these sets. So the type has to be present both in the query and among all the correct answers to be defined as the correct type. Our approach is to use a syntactic parser that we run on the query to determine the structure of the query and hopefully differentiate between head words, like in this case, movies about presidents. Movies is the head word, which makes this type more likely to be correct as this one. Or in the longer query, tennis players who wore denim shorts, the player is the head word, which means the correct type is a person or a athlete or something like that. Here's an animation on how the syntactic parser works. It's a transition-based system where there's a stack and a buffer, and at any point of time there's a choice between certain actions where we can take an item from a buffer onto the stack or add left arcs or right arcs. And the feed-forward neural network assigns probabilities to these actions, which means that the network that determines the parse structure is an end-to-end differentiable model. Here's a more precise overview of the network architecture. We have a set of features based on the current situation and the words that we are considering, and the feed-forward neural network determines which probabilities assigned to which actions and consequently to which parse structures. Here are some stats about our dataset. So first, we clearly need a type inventory, and for that we use Freebase or knowledge graph collections, which is the same thing. And we also need labeled query answer pairs, for which we use Facebook's simple questions. It contains 76,000 questions and 36,000 unique answers. Most of them have knowledge graph collections. And here is the distribution of the number of correct types per query. So clearly the most frequent case is either not having found the correct type or having just a few correct types, but then there's also a heavy tail as well. Here are the numbers of our experiments. So first is the full type vocabulary. And by the way, the models are evaluated using sigmoid cross-entropy, and we use sigmoid because types are not exclusive of one another. So the first model just outputs all the tokens found in the query that are types within the inventory. The second model uses the same input as the previous one, but runs logistic regression to predict every answer type independently. And then the final model is a syntactic parser, which assigns probabilities to query parse trees and based on that feeds features into the sigmoid layer. Clearly, the easiest baseline has the highest loss function, and the simpler baseline has a somewhat smaller. But the syntactic parser did not fit into RAM for the full type vocabulary, so I had to throw out all the types that were not present as correct type at least once, which was supposed to increase the loss function, but surprisingly it actually decreased. So here we see that the syntactic parser is a clear winner among these models. But an interesting thing that I decided to investigate is whether it would get an even higher advantage on more complicated queries. So the number of slots in the query is simply the number of tokens that are somehow related to a type. So for example, if the query is movies about presidents, there would be 2 slots because both movies and presidents are types within our type inventory. The surprising finding is that the more slots we have in the query, the less is actually the difference between the simple logistic regression and the features produced by syntactic parser. This is surprising and clearly needs further investigation. And another direction which I want to explore is fine-tuning the weights of the dependency parser specifically on QA-related data.